for coming to the session today. My name is Geeta Chauhan, and today I will be talking to you about deep learning in the medical imaging space. Greg already did a brief synopsis of the agenda, so I'll be talking about the use cases for deep learning in medical imaging. And for those of you who may not know what deep learning is, we will do a brief intro into deep learning. And we will look at some of the models that are used for medical imaging in deep learning. And then we will look at the rise of the spatialized compute, which is being fueled by deep learning, and how you can, some of the techniques for optimizing both your models at the training time and at the inferencing time. Then we will look at end-to-end pipeline. If you're building one for your machine learning platform, what are some good strategies for that? We will look at what is coming down on the horizon in the future, and where you can start your journey in the medical imaging space, if that's an area that you're interested in. So this here is a map of the startups from CV Insights. So they have put together startups in the healthcare space that are using AI. And at the top right corner, you will see all the companies in the imaging, medical imaging and diagnostic space. So this is a very hot area. A lot of investment is happening. And according to IBM, 90% of all data in the medical space, in the healthcare space, is in medical images. So it's a lot of opportunity to use deep learning in this area. So these are some of the areas where these startups are working with deep learning in medical imaging. So Analytic is a company that is doing real-time clinical diagnostics using deep learning. So it's making it available to the physicians as they are in their practicing office, making all the data accessible and the insights from the data to them while they are working with a patient. And there are a bunch of companies, Butterfly Networks, Bay Labs, who are betting on the portable ultrasound. So they have like a device that you can plug into your iPhone or your Android, and you can do ultrasound of the patient wherever the point of care of the physician is. So you're not tied to having to bring an ultrasound machine into the operating room, or so it gives a lot of flexibility to the physicians. And there are a bunch of companies that are focusing on cloud imaging, AI. So they are, like providing like an assistant for the radiologist to quickly look at the images, decipher what is going on, and people can do it in a 3D volumetric flow. They can get, it's very interactive and much more easier to use than the traditional X-rays or MRIs that you guys may have seen. Okay. Companies like Zebra and Artsys. And another company is focusing just on the stroke. So they're offering an intelligent stroke care based on AI. And then a bunch of companies, including Google, IBM, Analytic, and many more, are looking at screening. So the opportunity here is that earlier you're able to diagnose many of the diseases. You can then take proactive action and nip the disease in the bud. So like if some diseases are diagnosed when they're just starting, you have a chance of curing the disease, versus if they're diagnosed at a much later stage, then the life expectancy is very small. So this includes use cases like diabetic retinopathy and detection of tumors, skin cancer, detection of lesions for Alzheimer's, Parkinson's, etc. And there's another company that's focusing just on oncology. They, in fact, got bought by Roche just a couple of months back. So this is Flatiron Health. So they are doing deep learning and other techniques just on the cancer research. Now, if you decide to come into the medical imaging space and use your data science skills, I would say that it is a very rewarding area because you can make a huge impact on society and your family, friends, etc. So if we take the example of skin cancer, there are 5.4 million cases of skin cancer diagnosed in US. 10,000 people lose their lives in US to skin cancer every year. 8 billion plus is the annual cost of skin cancer. And if you take a look at that graph, you see the different stages. The image on the left-hand side is when it is early, the one with the 0 on top, and the one with the 4 on top is when you detect it very late, so it's already penetrated pretty late. So if you're doing the detection at stage 1, your life expectancy is almost 100%. But if you were to diagnose the skin cancer at stage 4, then less than 20% your life expectancy, like you will just live for 5 years, less than 20%. So it goes down such a lot. So early diagnosis is what is the key, and this is what the companies are targeting with deep learning. So these are some of the successes with deep learning, where deep learning has already achieved state-of-the-art compared to what is there in the medical space. So you see all these images. There's this mammographic mass classification. Next one is the brain lesions for Alzheimer's. Then there is the airway leakages in your lungs. There are leakages. Then diabetic retinopathy. Then prostate segmentation for being able to detect prostate cancer. Then on the breast cancer metastasis, skin lesions classifications. And the last one at the bottom is an interesting one. So for many diseases in the chest, you take a full X-ray of your chest. Now all these bones that we have, our rib cage, that kind of occludes what is behind. So one interesting technique that is used is for bone suppression. So you are basically eliminating the bones from the image. And then you are able to see what is behind the bones and decipher what the actual problem is. So how many people here are already into deep learning? That's sizable. So for those of you who are not familiar with deep learning, it is a technique where you are building neural networks. You're basically stacking these layers of networks and passing the data through them, and you are deciphering the hidden latent features in your data just by processing the data. So you don't have to do feature engineering, unlike in the past that you had to do for machine learning. Okay? So the deep learning models, the neural networks, they learn like humans. So just like when you were learning how to drive a car, you would try out many things. So that's how the deep learning models learn. And if you see the images at the bottom, so this neural network is trying to recognize a face. The earlier layers in the network are like, all the layers in the network are like image filters. The earlier layers will detect higher level features like the edges, the lower level features, and then as you go to the deeper layers, they combine these features together, and then you are able to get to the last layer is able to detect different parts of the face. Okay. So this is a nice paper that came out last year doing a survey of deep learning in the medical imaging. So this looked at 300 plus papers that were published and did an analysis of how deep learning is being used in the medical imaging space. So the last 2 years there is a lot of activity. Many companies have started to jump into this area, and it's being used for all types of medical imaging. So be it MRI, CT scans, ultrasounds, X-rays, etc. So all types. And there are main categories where you're trying to do either a classification of the exam, so you're trying to figure out whether someone has a disease or not, or you could be doing a detection of the object, so like where exactly your different parts of your heart are, so you're doing that object segmentation. And then you could be, like in the case of brain lesions that you saw, you could be segmenting the areas where the lesions are. And there's another interesting technique for registration. So this is doing the spatial alignment. So when you're looking at multiple images for the same disease, you want to be able to see the structure across all the images. So there's a special technique, registration, that is used. So these are, let's look at some of the models that are used in the medical imaging space. Many people are using models like GoogleNet, AlexNet, VGG19, etc. So this is a good place to start, especially if you have limited data set. So you're taking these pre-trained models and using transfer learning to get the first level of analysis from the models. Now the challenges in the medical imaging space is that unlike the other imaging, the actual number of data points is much less because the annotation is very hard to do. It requires a clinician to go and annotate the images, which can be very costly. So that's the big challenge that the medical imaging space has to deal with. And then the other challenge is the size of the images. Size of the images is very large compared to, like, if you're taking an image of a dog or a cat, etc. So these images tend to be much larger. And when you're taking an image of like people, photographing people or dogs or cats, you're focusing on an object and taking the image. But in the case of medical space, you're like taking an X-ray of your chest. So it's like whole body, and then you have to figure out what is there inside the chest. So you're not like putting your focus in one particular spot and taking the image of that. So that's a big difference. So some models have come up. UNet, VNet, ENet are some example models where people are using fully convolutional networks with skip connections to deal with this issue of less amount of data. A lot of data augmentation is used, so you're flipping the images, transforming, etc. And so this model here, the picture that you see, this is the picture of the UNet model. So with the size of the image is much larger, you don't have to do tiling of the image, you can feed in your entire image in one shot, and at the end get the results. Okay? So this, at the top you see an example of how they're doing the segmentation in the cell cytoplasm. Then other set of models are coming where they're combining CNNs with RNNs. So there's a paper that just came out, Tynet, and another one from Analytic on the dense CNN, where they're using a dense CNN encoder followed by a RNN decoder for doing the multi-label classification. Then for the image registration space, people are using this fully convolutional networks along with reinforcement learning for doing the spatial alignment of the images. This is the Tynet paper where they're taking the chest X-rays and then spitting out the labels for what is there in the image. This one is a paper came out from NIH early this year. Okay. So with deep learning taking off past few years, I'm observing a huge shift in the industry where we are moving towards spatialized compute. So this trend is visible in all the cloud vendors. Google is using their tensor processing units. Microsoft has announced their project Brainwave. Intel, their Nirvana Cloud. IBM has their Power AI, and NVIDIA's B100 came out recently. And then cloud vendors are also going towards bare metal cloud. So Amazon announced bare metal cloud at their conference in November, and Google soon followed suit and announced that they will be launching, and their bare metal cloud will be available starting from next month. So there's a huge spectrum here. So you go from CPUs and GPUs to FPGAs and custom ASICs. So CPUs, GPUs offer you general purpose computing, whereas if you go to a custom ASICs, you're designing a chip especially for the use case that you're targeting. Okay. Many companies have also started coming out with AI system on chips, and you will see in the coming years, like this year and next year, more and more companies coming out with AI chips. So some places that people have already started is Intel's neural compute stick, which is a USB stick with a vision processing unit on top. NVIDIA has their Jetson, which is also a very small form factor, size of a credit card. And then NVIDIA's Drive PX for the self-driving car. And on the architecture sides, the cluster compute has started to take off. So, these are the Kubernetes, Apache Mesos, cluster computing. And then we are starting to see a convergence of the HPC world with deep learning. So, so traditionally HPC has been used in the scientific domain. Now it is starting to come into the enterprises as well. And in the future, we will have Neuromorphic and the quantum compute. So more and more complexity is in the software now. The models are very specific. The model tuning and optimization is to be done very specific to the hardware. There's a strong need for building compilers. This is a pain point area right now, because if you want to deploy a model, when you're training your model, you require a different set of hardware, so you have to tune your pipeline for that. When you're deploying it for inferencing, for the predictions, you need to do a different level of tuning. And then again for the workload specific. So all the burden right now is on the data scientist. And the companies should be, like companies like Google, IBM, Amazon should be looking at building better compilers. So now I will dive into some of the optimization areas. So a lot of people talk about GPUs in the context of deep learning, but not many people are familiar with how you can optimize your CPUs, what you already have in your data centers, and get up to 72x speed up on your existing hardware just by using the right kind of optimized tool chains. So if you are building, so you need to leverage high performance computing tools. So on the Intel, use the Intel Python, which is optimized for running on Intel CPUs. Use Intel's math kernel library, and there's also NNPAC, which came out of Georgia Tech, which is multi-core, which supports across multiple architectures of CPUs. If you're doing your model training with TensorFlow, compile it from source to get the best results. Make sure you're using proper batch sizing that are utilizing all the cores and memory on your machine. Make sure you're using the right data format. So if you are doing your model training on a CPU, it is better to use NCHW format for the images, where N is your batch size, C is the color channel and the height and width, versus the default which comes out of box for TensorFlow, which is NHWC, which is optimized for GPUs. And when you're reading your data, make sure that you're loading it up into queues, so that as your model are going through each iteration, you already have queued up the data for the next round. And if you were to apply all these techniques, you can, depending upon the current hardware, for the same model, you can get up to 72x speed up. So this is a benchmark coming out of Intel. So These are the steps if you wanted to compile TensorFlow from source for your CPU. So you basically git clone the TensorFlow repo onto your machine, run the configure command, and make sure that you select the MKL CPU Optimizations option. And then you build, so the Bazel is the tool that Google uses for building TensorFlow. So you will run the Bazel build command and generate the pip package, which will create the wheel file that you can install. Now, the good thing is that Intel has also started publishing some of these pip wheel files for specific architectures. So you don't always have to compile from source on your machine. So you could, like if a version is available, you can go to the Intel site and get that and use that as a starting point. Okay, so any questions so far? Okay. So let's dive into techniques for parallelizing your models. There are two primary methodologies. One is data parallelism and the other is model parallelism. In the case of data parallelism, you are partitioning your data into chunks, and then each partition then processes just that data, and then you are getting all the shared model state in parameter servers and combining and getting the results. In the case of model parallelism, you are taking your model, different layers of your model, so like in the deep neural network, you are chunking and running each layer on a different machine and getting the results from that. So in the TensorFlow, there is this concept of model towers if you're using model parallelism. You would typically use model parallelism if your graph is very large and not able to fit on a single machine. However, model parallelism is quite challenging and generally not used in the industry. Most people are able to do majority of their work using data parallelism. So if you're starting new on deep learning side, I would suggest start with data parallelism, and once you've built good number of models, it will be a good time to tackle model parallelism. Now, there are few besides TensorFlow. So TensorFlow gives a good level of tooling for data parallelism. If you use the high-level estimator and experiments, it kind of hides away a lot of this complexity of chunking and running on the different parallel machines. TensorFlow has this concept of parameter server and worker cluster, so you can collect all your model, all the parameters in one centralized space and get all the weights optimized over there. If you're coming from the Spark Hadoop world, I would suggest look at Intel's Big DL, which runs on the Spark cluster. So this will be a much easier starting point for you. And other companies who have built frameworks here is Baidu has built a ring all reduced framework where they are doing the optimization across the GPUs. So all the GPUs are put in a ring configuration, and instead of sending all your model weights to every GPU, they're just sending it to the next neighbor in the ring. So they're able to optimize with that. Uber has recently open sourced their Horwood Tensor Fusion for distributed TensorFlow running. So you're basically just building your model as if you're doing it for a single GPU, and you can get the automatic parallelism through this framework. And if you're using the Google Cloud, you can rely on the hypertune features of Google Cloud ML. So these are not available in the open source TensorFlow. So you have to use the Google's Cloud ML to use these features.
What does hypertune do? Is it tuning architecture, changing number of hidden nodes, or?
So the hypertune is tuning the hyperparameters. So you're basically instrumenting your model when you're doing your training, And then it will give you the recommendations for how to optimize your hyperparameters for the model training.
Okay. A bit like learning rate, momentum, kind of hyperparameters?
Yes, yes.
Okay.
Then looking at some techniques for optimizations during the training. So if your model is large and it's not able to fit into the memory of a single machine, you can use this technique where you are segmenting your model, and instead of doing the computing and storing all the weights in the forward pass, you're only storing the head node results and then doing recomputation when you're coming for the backward pass. So with this you can get an order of square root of n, speed up, and you're able to process much larger models on the same piece of hardware. So the paper that talks more about it in detail. When you're partitioning your workloads across the GPUs, you need to keep in mind that you have to basically minimize the communication time for the weights. You would place neighboring layers on the same GPU where possible. You try to balance the workload across the GPUs. So if you're using 8 GPUs, so don't like overburden one GPU and then leave another one totally idle. So different layers in the network have different memory and compute properties, so you need to be aware of that when you're using your workload partitioning. So in this example here, we have LSTMs and the encoder and the decoder layer. The LSTMs require less memory but take more computation time, whereas the encoder decoder require more memory. So if you partition, if you see, like you will see the dot 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 for the separation. So if you partition the model like the one on the left, that is much more balanced versus the one on the right. So how you segment and put your layers across the GPUs, that matters. Okay. So now coming to some of the optimizations for the inferencing time. So this is when you are running your models for prediction at runtime. TensorFlow has a tool called the graph transform tool. So you can use that to optimize your models for runtime. So if you take a look at this picture, who here can tell what picture this is? Whose picture is this?
Vincent Van Gogh.
Vincent Van Gogh, that's right. So even though it's a very low resolution picture of Van Gogh, we can still make out that it's a Van Gogh. So similar thing applies when you're compressing your models in deep learning for inferencing. So deep learning is fairly tolerant to noise in the network, and even with the compression, you're still able to get fairly similar levels of accuracy and results. Okay. So some of the techniques are, you will freeze the graph where you are freezing the variables which are only used during the training time and replacing them with constants because you don't need those variables at runtime, so just the constant values would suffice. Then another technique is quantization, where you are replacing 32-bit float computations with 8-bit integer computations. So if you take a model like the Inception V3 and you applied quantization of weights, where it has 20 million weights, just by using quantization, you can reduce your model from 3.9 megabytes to 1.5 megabytes. And you can basically run it on your Raspberry Pi after that. So the model becomes so small. And there's a very nice paper, Deep Compression. I have the link in the references, which talks about combining few techniques together. So using pruning for certain nodes which are not relevant in the inferencing time, sharing of weights across the layers, and then applying some deep compression techniques. They were able to get AlexNet 35x smaller VGG 1649x smaller, and with 3 to 4x speed up and 3 to 7x more energy efficiency with less than 1% loss in accuracy. So very little loss in accuracy and still getting such good results. So at the inference time, your whole goal is, if you're serving your models in the cloud, how many predictions you can do, like how many users you can support in parallel using the same piece of hardware. So if you're requiring lots and lots of hardware just to do each model computation, it will not be very practical in the field. So that's why you want to compress and use these techniques.
Can I ask a question about that?
Sure.
I know the work that you just mentioned trained the network and then compressed it by running all the training examples through again. If you're starting with AlexNet and replacing the last layers to customize it, for example, can you get that reduction in the system you end up with without sort of having to go through the full CFAR million data set?
So let me understand. Are you asking this in the context of transfer learning or in the context of inferencing optimizations?
In the context of compressing the network for faster evaluation and smaller.
So the question is so when would you do the compression for the faster inferencing for the predictions? So you do this after your model has already been trained. So if you were using transfer learning, you would have already taken GoogleNet or AlexNet as your base. You strip off the last layer, put your own layer, train that model. So after you have this entire model trained, that's when you would apply the compressing techniques and run this like the graph transform tool and do the optimizations. So you don't do the optimizations on BGGNet first, then do transfer learning. So you build your model and then in the end you do the optimizations.
And then you run your own training examples through.
Yes.
Yeah.
Okay.
Okay.
Yeah. So you don't have to rerun your training examples after you do the compression. So all the training examples are done prior to that. So in the training phase, you would have taken all your data, ran through it. Once you are ready, sure, okay, this is the final model, this is what I want to deploy in production. That's when you take that model and then do the compression for it for deploying in production.
But the model that works well is mostly offline training. But if you have to have an online training pipeline, we often using a data model. Is there another workflow that you can follow to get the benefit of the regression, or do you have always to retrain from the original model, then you convert into lighter version?
Yes, so there are techniques for that. I actually cover it as part of the end-to-end pipeline. So the question was, if you're doing a continuous model training, so your model is deployed in production and you need to retrain the model with new data sets, what are some, so I'll cover that in one of the next slides. Any other questions? Okay. So now looking at some of the optimizations for your clusters. So if you are not using Docker containers already, I highly recommend that you switch to Docker containers for all your machine learning work. I suggest building your base container locally on your workstation first, and then deploy it in the cloud with the different parameters for optimizing and tuning. If you're using the Amazon cloud, for example, make sure you're using the Elastic file system. With Google Cloud, use the Google Files system, so your data storage, so you're basically sharing your data across the nodes and not having to make a copy of the data, which is a very expensive process. And you can use techniques for avoiding GPU fragmentation by bundling all your jobs together. So if you're using Kubernetes, it has this placement optimizations. Same with Apache Mesos, so you can use the placement constraints. And if you're coming from the HPC side, there are techniques similar for over there. So you bundle basically all your related things as a single pod, and then you do the machine learning training on that. And if you're using GPUs, one big challenge with Docker containers is how you would get your CUDA drivers with the Docker container. So you can either go with the NVIDIA Docker, both Kubernetes and Mesos have support for this now, or you can mount your drivers as a read-only volume. So if you mount your drivers as a read-only volume, you get the added advantage of being able to work with different runtime libraries. So you could be working with CUDA 9 or early versions. Just change your volume link and you can use the appropriate version according to the GPUs. So I talked briefly about the Uber's Horwood, which they open source. So it is part of their bigger Michelangelo platform. There's actually a very nice blog post on Uber's engineering site, so I highly recommend that you guys go take a look at that. So they have built a gang scheduler with Apache Mesos. It's called the Peloton Gang Scheduler. Unfortunately, they haven't open sourced this yet. So what this gang scheduler allows them to do is, if they have a training job, which let's say requires 10 GPUs, so they are able to schedule all these 10 GPUs as a single shot, so as a gang, using this. Otherwise, like if you were using plain vanilla Mesos or Kubernetes, you don't have that level of control. They're using MPI for all the communication optimization for the bandwidth. With the Horwood, you just need to code as if you were working on a single GPU, and it will automatically parallelize for the other GPUs. Another interesting part of their architecture is this notion of nested containers. So they have these outer management containers in which your actual machine learning container gets deployed, and then their Michelangelo platform is managing all the outer, and the data scientist just needs to package their container with the models and as part of the worker container, and it automatically gets scaled up. So this will be a good architecture to look at if you're looking to build your own platform. Okay. Now looking at the end-to-end pipeline, so for your question, Google came out with their TFX paper. I believe they presented it at KDD last year. So this is targeting continuous training and serving of the model. So they are looking at all aspects, so it just doesn't look at just the model training and inferencing part, but management of your data is a big part of it. So analysis of the data, transformation, validation, making sure automatic tools are available to the data scientists for this, and they are checking the sanity of the data and making those insights available. Then they have this notion of a warm startup. So when you are retraining your model the second time over, so when you're in a continuous training loop, so instead of starting your training from scratch all over again, they start from a pre-trained general checkpoint version, and they use that to jumpstart for the next round when they are retraining their models. So I highly recommend that you go look at this, the warm startup technique on this paper. And also look at the similar pipeline, or the Michelangelo pipeline from Uber to get further ideas. Okay. Now, one of the big complaints that people have about deep learning is that it's a black box. So this is an active area of research. DARPA launched a whole initiative called Explainable AI last year, where they are looking at techniques for how you can make your model explainable. So, like if you see recommendation to a physician that, model detected this, they ought to be able to decipher why, how that decision was made, why that was made, and why that recommendation was given. So there are a few things which are already available in this space. So you can use activation heat maps for your models to figure out, what part of the image actually excited and gave the classification result. Similarly, you can look at saliency maps. And then techniques that are used in medical imaging, people are trying to reconstruct the original image to get the coarse features of what was detected really from that image. That's a technique many people are using in medical imaging space. And then if you're doing classification, then T-SNE visualizations will be good ones. And if you're using TensorBoard has a very good T-SNE visualization tool. I highly recommend using that. Then more things in the future. Microsoft announced their project Brainwave last year, and just like we have microservices for building our software, Microsoft is saying that the next wave would be hardware microservices. So on the FPGA, you can put any custom logic. So you are basically putting your whole data pipeline on the FPGA itself. So you have the FPGA, you put all your custom logic into the different blocks, and then you are taking your data across that. So if you can put your entire model onto the FPGA, then you won't even have to hit the CPU for when you are doing your predictions and doing the executions. So some companies have already started to use this in the genomic space. So for the whole body genome, they are using FPGAs to reduce the time for doing the predictions. So it's able to do the processing in 1 hour versus more than a day when the same model is deployed in FPGAs.
What does FPGA stand for?
Field programmable gate arrays, I think.
Question?
Yes.
So can you please explain a little bit about how programmable hardware such as FPGA are actually contributing to deep learning? I mean, I do understand you have programmable hardware, but in particular to what we're talking about deep learning, well, what is the big benefit then?
So the
Repeat
big
that question.
benefit. Yes, so the question is, what is the benefit of FPGAs in deep learning? Okay, so the big place where FPGAs are used in deep learning is in the inferencing space. So when you're doing your model predictions at runtime in production environment, that's when you've already built your model and you're putting all your model logic onto the FPGAs, and it is getting faster, it is doing the faster processing. That's where you see the biggest benefit. Okay. Some companies have also started to explore FPGAs for doing model training. So this is still early stages. There are a couple of papers already published where people are claiming that FPGAs are better than GPUs because they use much less energy. They are much more optimized because you're putting the custom logic for that specific model onto the FPGA, so you're able to do much faster, much better computations. You're not limited to the tool set that the GPU provides to you. So if you need to do a custom math calculation, you can put your custom logic on the FPGA and do that computation much faster.
So is there any GPU, the TPU that I think for the Google's one is either regular or for the TPU?
So in the
Repeat your
TPU, so the question is how, is anything similar there in the TPUs, like the GPUs? So Google has built their TPUs to optimize for tensor processing. So the first version of the TPUs was only targeting inferencing, so they were not doing any model training in the first version. In the current version, which is now available to the research community. So you have to be, sign up as a researcher. It's not open access right now, so it's only by invitation. So if Google invites you onto that, so you can also do the model training part on that. So they're, similar to what NVIDIA is doing with their V100s, they have added this logic for doing tensor processing at the hardware level itself, at the chip level itself. So basically the main reason why Google came up with the TPUs was cost of GPUs was very high. So by going to TPUs, they saved having to build 2 to 3 new data centers. Then they started with this TPU effort. So it's mainly for the cost. So FPGAs are much more energy efficient, and Google has put some similar techniques in their TPUs, which are basically a custom ASICs. Then further in the coming horizon is the neuromorphic compute. Intel launched their Lohi chips in December last year. So this is at present only available to select research institutions. So where they make use of memristors, which are combining both analog and digital, and basically it works like the human neuron. So we have synapses in the brain where the connections get strengthened as they get used. So similar things happen in the neuromorphic compute. And then further down the horizon is quantum computers. IBM has already made available a small qubit version of their quantum computers on the cloud for the research community. So anyone can go sign up and start experimenting. So with quantum computers, you will be able to do vast amount of processing, much more than what is possible today, and even tackle complex use cases like being able to do personalized medicines for cancer treatment. So in the case of cancer, the speed of doing the treatment is very important. And at present, being able to personalize this for each and every individual is not possible because of the cost and the computation that is required to come up with the personalized recommendations for a specific user. Then some downsides to the quantum computer, of course, are in the field of cybersecurity. So people are saying that once quantum computers come out, all our current security will be thrashed. Nobody will be able to break all the current codes, so we'll have to come up with new ways of securing our software. So if you're looking to start in the medical imaging space, there are many open data sets available. Many competitions are happening. So Cancer Image Archive has many data sets for the different types of cancers. Many competitions happen on Kaggle, like the diabetic retinopathy. The Data Science Bowl of last year was on lung cancer, and there's another Data Science Bowl that is going on at present for the cell nucleus. Then skin cancer data sets through ISIC, and there are other grand challenges for medical image analysis and some more links. So if you are starting your journey new in the medical imaging space and looking to use deep learning, I would highly recommend that you start with one of the Kaggle or other open competitions. So pick the data set from there. Use one of the pre-existing models like GoogleNet, AlexNet as a starting point. So start with transfer learning. And then as you have built few models with that, next stage would be to experiment with models specific to the medical imaging space like the UNet, VNet, etc. And then start to combine data from other sources for richer models. Then as you get to the next advanced level, that's when you can start building your models from scratch. so come up with new architectures. And as you go towards the maturity level, that's where you would do the continuous learning feedback loop. So you would build a ML platform where you're continuously training and deploying models and updating it in the field. So there, I also suggest experimenting with deep reinforcement learning. OpenAI Gym would be a good place to start if that's what you are looking to explore. And you basically are looking to industrialize your machine learning and deep learning pipelines. So similar techniques to as what is being used in the software engineering side with DevOps. You need to start inculcating those practices for your machine learning and deep learning as well. So it's not just your data scientists coming up with a Jupyter notebook and throwing it off the wall. You have to industrialize it, package it properly in a Docker container, make sure that the experiment results are repeatable, and someone other than the data scientist is actually able to use and reproduce, and you are able to quantify and measure your models themselves. So as you go from one iteration of the model to the next iteration, what are the improvements that you're seeing? So the traditional software engineering best practices have to be brought to machine learning and deep learning. So these are some of the references to the various things mentioned. Any more questions?
So the being a data scientist in this image processing, I mean, they need anything medical related they know, or any PhD required for being a data science in the image processing?
So I would say that now it's time to start to democratize data science. So the question is, do you need a PhD to be able to, do the medical imaging processing? So, participate in these Kaggle or other open competitions. Build up your skills in this space. Do something good with your time instead of, spending your energies building another model for how to sell more things to people. Advertisement, trading is where a lot of the data scientists are going today. So with this, you can make an impact on humanity, impact on the world. So I would encourage people to, even if you know nothing about the medical science space, you can pick it up.
Question?
For the reference that you gave for the medical imaging, one particular area that I've been seeking and not been successful so far is on the cardiac space. Do you have any ideas or suggestions on getting some data in cardiac space?
Yeah, so if you go to this and more the last link.
Question?
So the question was, where can you get data sets for the cardiac space? So if you go to the last link here, it has a much longer list. It includes, data sets from cardiac space as well.
So, question on your data sets. Since you're talking about medical diagnosis, which can be very specific based on race, gender, how do you, at that level of screening, before you adopt an entire data set for your specific application? I mean, like you said, if you're doing cardiac, it won't help to be looking at 98 percentile Caucasian if data is completely different for Asian.
Yeah, so the question is in the medical imaging space, how do you get the the race, gender, and other data points for the images? Because without that, it would be difficult to do the data analysis. So the good thing is that in the medical imaging space, the de facto standard pretty much is the DICOM for the images. All your X-rays, MRIs, they're stored in this format. And this stores also the patient information, so the high-level characteristics, like their age, gender, etc. So when you get all these data sets, from the DICOM image, you are able to take out these attributes about the patient. And in the annotated data sets that are available, all such parameters are made available.
I just want to add one more resource that deep learning community is so open. They always publish on archive.org.
Archive, yeah.
So it's good to know, because if you want to know better about specific type of segmentation or new data set, you just enter that on the website and there will be papers that mention that.
Yes, so Archive is a good source if you want to look at papers for the specific area that you're looking at. Now, one of the challenges in the medical space is not all the papers that get published. People don't publish their data sets, so they may be claiming very good results, which may be very specific to the narrow data set that they have. So when you're reading the papers, you ought to be able to decipher that as you're looking at the paper. So if it's a peer-reviewed paper cited by many other papers, that would be a good one to go and adopt, at least for your initial models. And for most benchmarks, it is best to reproduce the benchmark with your data instead of just blindly relying on the paper. Just because there's a paper published on Archive, the quality of different papers is not the same in the medical imaging space. Yes.
You talked about data parallelism and model parallelism, right? In terms of data parallelism, at the stage of feature engineering, model construction, and the model scoring, right? Sort of the iterative process of before you actually go to production. How effective these things are in terms of speeding things up?
So the question is, how effective are the techniques for data parallelism and speeding up in this model, feature engineering, training, and scoring space? So first of all, if you're coming from traditional machine learning to deep learning, there is no feature engineering in deep learning. All the features are derived from the data. And this data parallelism, model parallelism, these come into play during the training time. So when you're training your model, because that's when you're feeding vast amounts of data into your model, that's where you're looking to parallelize. So it's basically trying to reduce the time taken for your model training. So some of the models, like all these GoogleNet, ResNet, etc. Some of these models, when they came out, the initial version, it took Google 1 month to train one version of their model. Okay, so which is a very long time. So now, of course, a lot of things have been optimized, a lot better frameworks are available. But by parallelizing, that's what you're basically trying to reduce the cycle time for your model training.
You said data parallelism is more effective than model.
Data parallelism is more prevalent and easier to use. Model parallelism is very hard to use, and not many people have the skill sets to do the model parallelism. So it's an acquired skill. With time, you can get to model parallelism.
Is there presently any research going on developing sort of a hybrid tool that, given all the pre-trained models we have now, can help you pick the right pre-trained model given sort of like a problem description, let's say a medical problem, so you pick the best tool to diagnose it? And to put it in perspective, imagine all the energy consumption that will go into training the same models over and over again. We don't want to repeat the mistakes of Bitcoin, right?
That's right. So the question is, is someone building this hyper search tool where you can plug in your data set and someone comes up with a recommendation of, okay, you can go use this model for this particular data set. Something like this does not exist today. I hope companies like Google, Facebook invest in this area. They're doing it internally inside their organization. So like the Google's TFX paper, Uber's Michelangelo, platform. Facebook has a similar platform for their in-house. So they are trying to build these machine learning platforms in-house now because machine learning is widely deployed inside their organizations, and we want to see this, like people not having to reinvent the same wheel over and over again. I hope over the course of this year and next year, we'll also start to see some of these tool chains and things becoming available in the open source community. Yes.
One of the challenges in transfer learning is that most of the models are trained on ImageNet or MS-DOCO, which are natural images. And it's very, very different from if you have in the medical world. Do you have any efforts to kind of have like something like MS-DOCO, ImageNet for medical images?
So there are few models like the IPAX model for the eyes, which is being used in the diabetic retinopathy. So there are models like that. So if you go to these, like the cancer imaging archive is putting up these models. Lung cancer, they published a big data set, I believe 25,000 plus data points last year. Then the data science bowl is another one where a lot of effort is being put into creating all these annotated models. ISIC skin cancer data sets. So a lot of, you're seeing pockets of such investments happening. And I suggest looking at the medical imaging data challenges, the competitions. So similar to the ImageNet, there are multiple of these competitions happening. So if you watch out for those, then you will start to see.
It's really good to get the trained models. That's really the thing, like you just want to download a trained model.
Yeah, I have not seen a pre-trained model for the medical imaging yet. So many people are using transfer learning where they have actually seen benefits of taking a VGGNet model and just applying it in their domain. So for example, for the skin lesions detection, and they got very good results just on that, which was quite surprising. So this paper was published in Nature last year. I have it in the links where that's the first thing that they did, and they got very good results. And then they trained the model from scratch to using the data set that they had collected.
So medical imaging is a very highly regulated field. Can you talk about what are the FDA regulations for the deep learning? Are there any deployed models?
Yes, so in the medical imaging space, it is a highly regulated field. You require FDA clearance for these models to be deployed. So if you take a look at the companies that I listed in the use cases slide, most of these companies have already got an FDA clearance for their deep learning models. Some of them have published papers on arXiv, like Analytic, Datasets and all. So if you go to their website, you will see people now claiming, for the cardio space, for the skin cancer space, many other, this ultrasound, many spaces they've already got an FDA clearance.
You were talking about the explainable AI, right? They say that the accuracy and the explainability of the model are inversely proportional. So in this field, when we have got regulations and you want to make the model very accurate, so how will the explainability of the model will get impacted, and how will you kind of take care of that issue?
So how will the regulations interplay with the explainability of the model? So actually the regulations are what is demanding the explainability. So in this medical imaging space and similarly in the finance sector, it is the regulations which ask for, if you have a decision taken, you ought to be able to explain why that decision was taken. So that's the driving force behind why explainability is needed. This is an active area of research, and many companies are all the big players are coming up, doing research in this space, and still figuring out how best to get to the explainable solutions.
I mean, just getting back to the same question here, which is, isn't part of the chat with the deep learning you can do classification, but a lot of times you're really trying to understand, where is the tumor, what's the size of the tumor, what's the feature basically, and I haven't seen anything that allows us to get to that point. Is that?
Yes. So if you, these companies are already coming up with where they're able to quantize, the size of the tumor, or so they're able to show those attributes. There was actually a very nice video. If I suggest going to the Arteris site, ARTERYS. They have a bunch of videos on their site, where they are showing, like 4D, so you can see real-time 4D flow across your heart, the different ventricles and how the blood is flowing in a patient, to be able to detect where the blockages could be. So they have gotten to that level. So, it's much more advanced than, what we typically see in a chest X-ray, which, a lot of us have seen, or our dental X-rays. Things have become very dynamic and interactive, so a lot of advanced tools are coming out. So go to any of these companies, the companies that I've listed here, go to any of their sites. Most of them have some good links to videos.
Actually, the same question that I was asking. So actually my question was, are the companies compromising on accuracy to get the explainability for the regulations?
So the question is, are companies compromising on accuracy to get the explainability? No, that is not the case. Especially in the medical imaging space, you can't go with such, so lower accuracy. So that will not be deployed in the field. You could make a tool with slightly lower accuracy available as a tool set to a physician, where you can say, the model has only 80% confidence that this is the case, then you leave it up to the human to decide. So that would be deployed in a human in the loop scenario. So no company is deploying models where they are blindly saying, oh, it's 100% accurate, and you can now just take a decision blindly on the basis of this. So we haven't reached that stage yet. Okay, so right now, all the tools are, assuming there is a human in the loop. Longer term, the goal is to, that many radiologists will not be needed. For example, if you are targeting the developing countries where the number of doctors is much less, so there in the field, a nurse practitioner would be able to use some of these tools and still be able to get a course level of diagnosis. But in the end, to do the actual prescription for your disease, you still have to go see a doctor.